Welcome back to the review of my channel. My phone is called EXE. Today we're going to look at volume and surface area of pyramids, cones, and spheres. So these are the remaining 3D shapes or solids that you need to know about. So pyramids. This figure shows a pyramid with its base A being a quadrilateral. And typically, there are infinitely many types of pyramids with different bases. So you can have a pyramid with a triangular base, a rectangular base, a pentagonal base, and so on. We can derive its volume as 1/3 times the area of its base times its height, where this height is distinguished here. Well, the surface area will be the area of the base plus sigma AT, where this thing shows the sum of the area of the slant triangles. And what I mean by that is these triangles that are leaning here. And actually, pyramids are formed by when you have, let's say we have a certain polygon right here, and then we have a certain point up here, and then we can just join the vertices of these polygons to this specific point, and there you have a pyramid. And this works with any polygons, no matter how many sides it has. Now the area of the slant triangles can be actually determined by using the Pythagorean theorem to find the height of each triangle, or probably any method you prefer. So that's just a bit of information there. And next we're going to talk about the volume and surface area of cones. So cones are actually pyramids with its base area being a circle. And we can derive its volume the same as a pyramid, except this area is a special area since it is a circle. So we can just substitute the area of a circle into our formula there. Now the surface area is actually A plus S, where A is the base area and S is the area of the curved surface. Now if you look at the net of a cone, it looks a little bit like this. Oops. Just about like that. So it has this circle there, but it also have this surface, and that we call this a curved surface. Now this curved surface is actually formalized as pi r s, where s is the slant length of this cone, so it is distinguished here. And just like the pyramid, this slant length can be determined by the Pythagorean theorem. So then we can just simplify this into this formula, and then we can factor out a pi r out of this. And after this, you can just substitute the value of s by using the Pythagorean theorem. So we have pi r times r plus the square of h squared plus r squared, where this expression is obtained by the Pythagorean theorem. Alright, so last but not least is a sphere. And although this is not a sphere, it looks like just a normal circle, but it is a sphere. So the volume of a sphere is denoted as 4/3 times pi times r cubed. And the surface area will be 4 pi r squared. And that's all about the formulas and stuff. And let's jump into some example questions. Starting off pretty easy, this is question 1. Find the volume and surface area of each figure below. Leave your answers in terms of pi if necessary. So if you have a pi in your calculation, it's just best to keep it B. Right. So for part A, it is a rectangular prism with its base being a square, since its side lengths of this base are all equal. So it is a rectangular prism with a square base which has a side length of 10 and the height of the pyramid is 12. So the volume of a pyramid is actually 1/3 times the area of the base times the height. That will be a third times the area of the base will be 10 squared, or in other words, it is just 100. The height will be 12. You can cancel this, leaving us with a 4, leaving us with 400 units cubed. For the surface area, it will be the area of the base plus the other 4 triangles. Now the area of the 4 triangles, well, recall that a formula for a triangle is a half times base times height, with its base being perpendicular to its height. So in this case, we know our base, which is 10. We don't quite know our height. And that is kind of a problem, but we can solve this by using the Pythagorean theorem. We can project a line towards this line, such that it is perpendicular. And the way that this point is presented here is that it is exactly at the middle of the square surface. So that means this length right here is actually a half times 10, which will be 5. And let me just draw another line to kind of like make your imaginations make sense. So let me name this point right here O, and this point here where it intersects this line BC, point P. So look at triangle TOP. It is a right angle triangle with OP being 5 and OT being 12. To solve for TP, we can just use the Pythagorean theorem, and after you do all of that calculation, you get that the length of TP will be 13. So that means the height of each triangle will be 13. Now that we get our height of our triangle, we're ready to calculate our surface area. Our surface area will be the area of the base, which is 10 squared or 100, plus 4 times, well, because we have 4 triangles, times the area of each triangle. So we have half times base times height, with its base being 10 and its height being 13, as we have found before. You can cancel these 2 with this 4. Say 13, let me just fix that. So that will be 100 plus, that will be 260, that will be 360 units square. For part B, this is a cube with its base radius 6 and height 8. Using our formulas that we have derived earlier, we have 1/3 times pi r squared times h. That will be 1/3 times pi times 6 squared, which is 36, times 8. This 3 can cancel with this 36, leaving us with 12, leaving us with a final answer of 96 pi units cubed. For the surface area of this cone, well, we know that it is pi r times r plus s, where s is this length here. but we really don't quite know the side length here. However, that is pretty easy to see. So look at this specific right angle triangle there. I'm gonna just draw it right here to give a better representation. So it has a base of 6 and a height of 8. So the question is, what is this length here, also known as S, which is the side length here. And after you do the Pythagorean theorem calculation, you get this is equal to 10. So it turns out that this S is equal to 10. Plugging in our variables, we have pi times 6, which is our radius, times in quantity 6 plus 10. Calculating this, you'll get 96 pi. And it's pretty fascinating that the volume of this cone is equal to the surface area of this cone as well. So that is it for question 1. Let's jump into question 2. Well, for question 2, this figure shows a net of a solid and the solid formed by the net. So the net is on the left hand side right here, and the solid form is the right hand side. And the solid looks like a triangular pyramid with its base being an equilateral triangle. Find the surface area of the solid formed. So let's just do part A first. That is pretty simple. So the surface area here, notice that all of these individual triangles are actually congruent to each other because they are equal in side lengths and they're also equal in area. Therefore, our surface area is 4 times the area of each triangle. And that would be 4 times a half times its base, which I'm just going to choose 6 times its height. And the problem comes here. We don't really know the height yet. So let's see what we can do here. Perhaps I'll just focus in on one triangle, one equilateral triangle with side length 6. Let me draw a perpendicular bisector with this length right here. So yeah, and here we can actually prove that this actually also bisects this side length. That means it divides this into 2 parts, and we can do this using congruences of triangles. So I just draw a triangle for more space, so we know this is an equilateral triangle here. So again, we can just draw a perpendicular bisector, and let's see here. We know that the angles in a equilateral triangle are also equal, which are equal to 60 degrees. That means this angle and this angle are equal. So that's one key. We also know that this side length is also equal to each other since they touch each other at these points, and therefore this side must be equal to both triangles. Not only that, we know that this and this sides are also equal due to the fact that it is an equilateral triangle. And by the side angle side theorem, we know that these 2 triangles here on the left and on the right are congruent. So that's just a quick proof of this. So therefore we have proven this. We can conclude that these 2 side lengths are 2 and 3 respectively. We can have this 6 written here, and let's see. We can use the Pythagorean theorem to find the height of this triangle, which will be the height will be square root of 6 squared minus 3 squared, which will be 36 minus 9, which is equal to square root of 27. Can rewrite 27 as 9 times 3. We can extract this 9 out of the square root to get 3 square root of 3. So it turns out that this height will be 3 square root of 3. So I just plug that in here. So 4 times a half times 6 times 3 square root of 3, which will be, as you can just cancel this and cancel this, get 3. That will be 36 square root of 3. There we go. For part B, it says that a sphere has the same surface area with the solid. Find the radius of the sphere correct to 3 decimal places. So I've calculated the surface area of our pyramid. We can actually set up an equation in terms of the radius of the sphere. And we call that the surface area of a sphere is written as 4 pi r squared. And we can just set this equal to 36 square root of 3. Dividing 4 pi on both sides, you get r squared is equal to 36 square root of 3 over 4 pi, which is also equal to 9 square root of 3 over pi. That means our radius will be equal to the square root of 9 times the square root of 3 over pi, which if you plug that in a calculator, you'll get approximately equal to 2.228. Correct to 3 decimal places, of course. So that is it for question 2. Let's jump into question 3. Alright, for question 3, this is the last question. A cone with base radius 21 centimeters and height 30 centimeters is filled with water. The height of the water is 20 centimeters. Taking pi equals 22 over 7, find the volume of the water inside the cone, and later on we need to find the height of the water with the same volume, but instead inside a cuboid tank with dimensions 10 centimeters times 10 centimeters times 200 centimeters. Alright, for easiness, I've drawn 2 diagrams, each representing parts A and B respectively. So for part A, it is the cone thingy. So as you can see, the dimensions are shown here. Now you may think that it's pretty easy to find the volume of the water inside the cone. It is the volume, let me just label the volume of water, I guess, is equal to the volume of the huge cone minus the volume of the small cone formed by the surface of the water. So this will be a third pi r squared, which will be 21 squared, times, let's see, the height will be 30. Let's just write the units on the front. And the volume for the small cone will be a third pi the radius of the small cube. However, that is a problem. We're not given the radius of the little cone formed by the surface of the water. And that's not typically a problem, but it is a pretty difficult problem to solve if we are not familiar with similar triangles. So as you can see, I've labeled 2 triangles in red, and let me just read through it for you right here. And let's compare this. So this side angle is 20, the whole side angle will be 30, and this little thing is 21. Alright, so let's see. We can compare the angles. So notice that we have both right angles there, so that's a pretty good sign. But also notice that these 2 line segments are actually parallel to each other, since they are perpendicular to the surfaces of the water and the cone, which are also both parallel. So therefore that's also parallel. But that actually gives us more information about the angles, since we know that this angle here is actually equal to this angle right here by the special angles in parallel lines intersected by transversal. And we also know that this angle is equal to this angle by itself, since it occupies one of the angles in both triangles. And what that tells us is that we have fulfilled our confirmations for the angle theorem for the similarities of two triangles. So we have fulfilled this, and therefore these triangles are similar. So let me just label some points first. So we have A, B, C, D, E. So triangle ABC is similar to triangle BDE. And what it tells us is that the ratios of the sides must be equal. So let's just say that we want to compare this line segment with this line segment. So we have 21 over DE, which is our unknown line segment, is equal to, let's see, well, we can just use the heights for our advantage here. So we have 21 as our base for the larger triangle. That means we can choose 30 as the base, the height of our larger triangle. Likewise, we can choose length BD here as our our height for the smaller triangle. And length BD is actually pretty simple to calculate, because the whole thing here is 30, and this little bit here is 20. Therefore, the remaining bit must be 10. So 30 over 10. And with this, you can calculate that the length of DE must be equal to 7. So that is pretty good. So let's just write that in our formula. So remember that length DE is actually the radius formed by the surface of the water in the cone. So that will be 7 squared times our height for our cone, which will be, again, just like we calculated last time, this will be 10 centimeters. And I'll just extract the units on the front. And after you compute this, you'll get an answer of 40,040 over 3 centimeters cubed. After we've taken the approximation of pi to be 22/7 and do all of the arithmetic stuff there. So let me just recheck out my answers. Yep, so this is the answer. Alright, so that's part A done. So for part B, what will be the height of the water with the same volume, but instead in a cuboid tank as shown on the right side here? So the cuboid tank with its base being a square with side lengths 10 centimeters, and then we have the height of the cuboid tank being 200 centimeters. And then we need to know what this height is, which is the height of our water inside this cuboid tank. Well, since we know we're using the same water and the same amount of water, well, that brings us that the volume of the water inside the cone is equal to the volume of the water inside the cuboid tank. So that means 40,040 over 3 is equal to the volume of the water in the tank, which actually forms a cuboid, which has base area of 10 centimeters times 10 centimeters, which will be 100 centimeters squared. However, I'm just going to write the units later on. Or I think I don't really need to rewrite the units here, but I'll probably just add it on the answer later. So anyways, the base area of our cuboid tank will be 100 centimeters squared, and our height of our cuboid formed by the water will be h, which is our unknown here. And this is pretty simple to calculate. We have h is equal to 40,040 over 300. And in case you want the decimal approximation, it is approximately 133.467, correct to 3 decimal places. And if you guys want to know what the true form is, it's actually a recurring decimal. So we 133.466666 and so on. So I can put a little dot there above the 6. And that concludes our video. So hope you guys enjoyed this. Please subscribe for more videos, and I'll see you guys in the next one. Goodbye.